We are going to the next session of study of real analysis and the properties of real numbers. So far we were discussing what are sequences of real numbers, and in this session we will be discussing something called the series of numbers of real numbers. So what is the main difference between a sequence and a series? For a sequence, if you remember, we had discussed or defined a sequence as a function from the set of all natural numbers to this set, the so called sequence of real numbers. For corresponding to 1 there will be a term, corresponding to 2 there will be a term, for 3 there will be a term, and so on, and we denoted the sequence as sequence of x1, x2, x3 and so on. If the terms of the sequence are added, then we get what is called a series. So a series is a summation of the terms of the sequence. So the first session in this series or in this section is finite series. The definition is as follows: the sum of a finite number of terms of a sequence xn of real numbers is said to be a finite series, and it is denoted as x1 plus x2 plus x3 plus etc. plus xn, and this is the notation which is used for representing a series. Sigma is usually the notation for sum. So we are adding the first n terms of the series, and so we are getting sigma I equal to 1 to n xi, and it is read as summation I equal to 1 to n xi. As examples we can see summation k equal to 1 to n k is equal to n into n plus 1 by 2, and summation k equal to 1 to n of k square is equal to n into n plus 1 into 2n plus 1 upon 6. So if you remember, we had used these two expressions for proving using mathematical induction. So this as a notation is given as summation k equal to 1 to n of k is equal to n into n plus 1 upon 2. When we expand this and express it as a mathematical expression, this is equivalent to writing summation k equal to 1 to n k on expansion gives you 1 plus 2 plus 3 plus etc. plus n. So this summation is equal to n into n plus 1 upon 2. We had proved this using mathematical induction. So remember that whatever comes after this sigma notation, we are putting values to the index. This k is called the index, and so k is equal to 1, we will put this 1 here. It is added to the next value of k, which is 2, which is added to the next value of k, which is 3, and so on up to the last value given on top, which is n. And summation k equal to 1 to n k square is equal to 1 square plus 2 square plus etc. up to n square, and that is nothing but n into n plus 1 into 2n plus 1 upon 6. So this is the usual notation or expansion of this summation as mathematical terms. So that is the example given. So as a prerequisite to the next session, we require some terms which are familiar to you, which you might have learned in the previous classes, but we should revisit them. The sum of the arithmetic series. Arithmetic series are series which are having terms with a common difference. So the terms are of the form x1 plus n minus 1 into d, where d is the common difference or d is the increment that we are giving to get the next term, and then the sum to n terms of the arithmetic series is given by this formula n upon 2, 2a plus n minus 1 into d. So, as a quick review, we can look at the proof of this result. So, an arithmetic series can be well written in the form of a plus d, a plus 2d, etc. because we are adding d to each term to get the next term. So, this is the usual representation of an arithmetic series, arithmetic sequence. So, as a series if we write, this will become a plus d plus a plus 2d plus etc. So, we need to find the sum of the n terms of the arithmetic series. So, what we require is to find is Sn. So, Sn we can write as a plus d plus a plus 2d plus etc. up to the nth term. Nth term I am writing it as some b, so that the just previous term will be b minus d and the just previous term to that will be b minus 2d, because from the last term or from this term n minus 1th term, in order to get the n term we have to add a d. So, the just previous term to b will be b minus d, the previous one will be b minus 2d. So, again Sn can be written in this form starting with b minus d, b minus 2d plus etc. a plus d plus a plus 2d by writing in the reverse order. So, if you add these two expressions together, what we get is twice Sn is equal to a plus b plus, again this d and this d will get cancelled, you will get a plus b plus, again you will get 2d and minus 2d getting cancelled, you will get a plus b plus etc. Last term also will be a plus b. So, how many a plus b's you are getting? You are getting n a plus b's, because initially you had added n terms. So, we can write twice Sn is equal to a plus b how many times? N times. Therefore, Sn is nothing but a plus b into n by 2, or that is same as n by 2 into a plus. Now, what was actually b? b was the nth term of arithmetic series, which is given by a plus n minus 1 times d. Therefore, we will be getting a plus n minus 1 times d. So, how many a's we are getting? 2a. So, that gives you n upon 2 into 2a plus n minus 1 into d, which is exactly what was given in the slide. Sn is equal to n upon 2, 2a plus n minus 1 into d. So, this is how we get the sum of the n terms of an arithmetic series. Now, as we had learned arithmetic series, we have also learned what is called a geometric series. So, geometric series, for arithmetic series we are incrementing each term, but for getting a geometric series we are multiplying with a constant term for the just preceding term to get the next term. So, that means the elements of or the terms of the sequence, underlying sequence will be of the form a r power n minus 1, with the first term being a, and r is called the common ratio, and the sum of the series or sum of the terms of the sequence collectively is called the geometric series. And if we take the first n terms, we will be getting something like this: a plus AR square plus etc. AR power n minus 1, and that is given in short as A into R power n minus 1 by R minus 1 or A into 1 minus R power n by 1 minus R. So generally in some textbooks we can see only this value A into 1 minus R power n by 1 minus R, that we can see. It is accordingly as the ratio is greater than 1 or the ratio is less than 1. So if it is greater than 1 or less than 1, even if you take this single expression, you will get both from that. But in some textbooks it is given as separate also. So we can quickly have a look into the proof of this one. For a geometric series, Sn we are going to find, as we have seen in the slide, A plus AR square plus etc. we are adding up to AR power n minus 1. Now if we multiply throughout with the R, with the common ratio, what do we get? Multiply this entirely with R. Multiply with R. We get Rsn is equal to Ra or AR, you can write AR plus AR square plus AR cube plus etc. Last term will be AR power n. So subtracting these two, we will be getting 1 minus R into Sn is equal to, this A won't get cancelled, but AR minus AR, these two terms will get cancelled. AR square will get cancelled with negative AR square, AR cube will get cancelled with negative AR cube, etc. AR power n minus 1 will be getting cancelled with a negative of AR power n minus 1, which is here, and this term remains. So only these two terms remains, that is A minus AR power n we will be getting finally. Therefore we can write Sn as A into 1 minus R power n upon 1 minus R. So if R is greater than 1, this will become negative and this also will become negative. That is why we are writing it as R power n minus 1 by R minus 1, as we had seen in the slide. So that gives you both the expressions, if R is greater than 1 as well as R is less than 1. Now the next important series which you have to keep in mind is arithmetico-geometric series, which is a combination of both arithmetic series and geometric series. So the terms of the series are of the form A plus n minus 1 d into R power n minus 1, and the summation is given by this formula. So a quick glance of the proof will give you some insight. So AG series we will write. AG series, the series of the form A plus D times R plus A plus D 2D into R square plus etc. is called the arithmetico-geometric series or arithmetic geometric series. So Sn is equal to A plus D times R plus A plus 2D R square plus etc. Last term, nth term will be A plus n minus 1 times D R power n minus 1. So again, as we had done in the case of geometric series, if we multiply with R, Sn will give you AR plus A plus D times R square plus A plus 2D times R cube plus etc. Last term will be A plus n minus 1 D R power n. So as we had done in the case of geometric series, we will subtract these two and on subtraction I will write the expression only, you can simplify it and find. So 1 minus r times Sn is equal to, a remains as such, a won't be getting cancelled, last term also remains as such, plus we will be having, it's plus or minus, plus, okay, and we will be having d into r plus r square plus etc. up to r minus 1 terms. So this is the expression which is obtained after simplification. So this is equal to a minus of a plus n minus 1 into d r power n plus dr we can take out, so that the rest becomes a geometric series with common ratio 1 and first term 1. So which on simplification gives you a minus of a plus n minus 1 times d r power n plus dr into 1 minus r power n minus 2 n minus, sorry, this is actually n minus 2, because we are taking, this will be n minus 2. So here it will be n minus 1. So you are getting an expression like this upon 1 minus r. So here already there is a 1 minus r into Sn here. So when you take this 1 minus r down, we will be getting a minus of a plus n minus 1 times d into r power n whole divided by 1 minus r plus dr times 1 minus r power n minus 1 upon 1 minus r the whole square, which is exactly given in the slide. So what did I write here? Yes, okay. So this is the sum to n terms of an arithmetic geometric series, which is a combination of both. So as a problem, you can see sum of the first n terms of the series sigma n by 2 power n. So looking at the series carefully, you can write the first few terms of the series and then you can understand. Summation n upon 2 power n, if you expand by putting different values of n, you will be getting 1 by 2 plus 1 by 2 square, sorry 2 by 2 square plus 3 by 2 cube plus etc. So we can see that there is an increment as well as the multiplication going on. So we can identify this to be an AG series. So once you have identified it to be an AG series, you need the first term, which is A. What is A? It is 1 by 2. What is R? R is also 1 by 2. What is D? D equal to 1. So simply putting the values of A, D and R in the sum to n terms Sn, you can get sum to n terms of the series is equal to A minus of A plus n minus 1 times D r raised to n upon 1 minus r plus dr into 1 minus r power n minus 1 by 1 minus r the whole square. Substituting, you will be getting the answer. So that is how we do a problem using the sum to n terms, the formula for sum to n terms, identifying the given series to be an AG series. So that is how we can solve this problem. Now the next important series which we have to keep in mind is called telescopic series. So what is known as telescopic series, or how is telescopic series obtained? This technique expresses the sum of n terms of a given series in just 2 terms, and usually it is the first and the last term, and all the intermediate terms are getting cancelled. So we will use some technique so that we can write the sum to n terms in a particular way, so that all the intermittent terms are getting cancelled. You will be getting only the first and the last term. So the last term, which was far away from the first term, becomes closer to the first term by this technique. and that is why this method is called telescopic. So, telescope is an instrument which takes objects very close to us. So, that is why the last term which was far away from the first term is made very close to the first term by using the cancellation of intermittent terms, and this process is what is called the telescopic summation. So, we can see some examples of telescopic series. First we will do this one, summation k equal to 1 to n of 1 upon root k plus root k plus 1. So, summation k equal to 1 to n 1 upon root k plus root of k plus 1. So, whenever you remember, whenever you have surds or radicals, sum of surds or sum of radicals which are the sum of the squares of numbers or difference of squares of numbers, usually you have to multiply with the conjugate before doing the operation given. So, we can write the nth term as 1 by root k plus root k plus 1, which is made equivalent by taking the conjugate multiplication, which is the conjugate of root k plus 1. This is one term plus another term. So, root k minus of root k plus 1 is the conjugate. So, on multiplication with both numerator and denominator with the conjugate term root k plus root k plus 1, which was already there, into the conjugate root k minus root of k plus 1, you are getting root k minus root of k plus 1 whole divided by k minus k plus 1, because it is of the form a plus b into a minus b, which gives you a square minus b square. So, you are having k minus of k plus 1, and on simplification you will be getting a negative 1 in the denominator, and so this can be written as root of k plus 1 minus root k. So, this expression which was given inside the summation sign is equivalent to root k plus 1 minus root k. That is what we have done here. So, instead of writing summation k equal to 1 to n 1 upon root k plus root of k plus 1, we can very well write it as summation k equal to 1 to n of root of k plus 1 minus root k. Now, you put different values for k. So, there is equal to square root of the first value of k is 1. So, 1 when you put, you will be getting root 2 minus root 1 plus the second value is 2. So, you can write root 3 minus root 2 plus the third value is 3, and so when you have root of 3 plus 1, that is root 4 minus root 3, and so on. The last nth term is root of n plus 1 minus root n. So, the just previous term also I will write for your understanding. If you put n minus 1 to k, you are getting the just previous term as root of n minus root of n minus 1. So, that is what we are getting just before this term. So, when you add all these terms, you can see that root 2 minus root 2 is getting cancelled, root 3 minus root 3 is cancelled, again root 4 minus root 4 is somewhere here, root 5 root minus 5, root 6 root minus 6 and negative root 6 and root 6 getting cancelled. Similarly, negative root n, negative root n minus 1 is also somewhere in between. So, only the two terms which are not getting cancelled are root of n plus 1 minus root 1. Root 1 is 1 itself. So, these two terms are the only two terms which are not getting cancelled, and so this expression we could write it as the difference between the last and the first term. So, that is why it is called a telescopic series. Now, the next example is given as summation k equal to 1 to n 1 by k into k plus 1. That again we can consider as a telescopic series. Summation k equal to 1 to n 1 upon k into k plus 1. So you may remember something called partial fraction you might have learned. So expressing the denominator, which is a product of two linear factors, we can write this term 1 upon k into k plus 1 as some number say a by k plus some number b by k plus 1. This technique you might have learned in schools. So taking the LCM and on simplification you will be getting a into k plus 1 plus bk upon k into k plus 1, which gives you a into k plus 1 plus bk is equal to 1, because the numerator and denominator should be equated. Denominator is the same, so numerators should also be equal. So a into k plus 1 plus bk is exactly equal to 1. So there are many techniques for finding what are a and b, and solving you will be getting a as 1 and b as minus 1 in this case. So summation k equal to 1 to n 1 upon k into k plus 1 can be represented as 1 upon k into k plus 1 is equal to 1 by k minus 1 by k plus 1. You will be getting a and b on simplification. So we can just check by taking the LCM. You will be getting k plus 1 minus k and k will get cancelled. You will be getting exactly same as this expression on the left side. Now if you apply this here, so this becomes summation k equal to 1 to n of 1 by k minus 1 by k plus 1, which gives you an expansion something like this. By putting different values of k, you can see the first term is 1 minus 1 by 2 plus 1 by 2 minus 1 by 3 plus etc. Last term will be 1 by n minus 1 minus 1 by n. So as we had discussed in the previous example, negative 1 by 2, 1 by 2, negative 1 by 3, all the intermittent terms will get cancelled. You are left with only two terms, 1 minus 1 by n. So this is the example that you have to keep in mind more than this one, because we need to apply all these prerequisites that we have learned so far for discussing more on series, and we are now going to see what is the sum to infinite number of terms of a given series. So that means if all the terms of the sequence are getting added indefinitely, what happens to the series? So that is what we are going to discuss in the next class. Thank you.